All right, welcome to part 9 of Robotic Arm Manipulation with Human Experiences in HRL. We are almost at the end here. This is the last video before we get into the end and bonus lessons. And today, what we're going to be doing is implementing the master training loop, the training loop for the meta agent, as well as some statistical a function to get us a percentage on how successful our agent is. So let's go ahead and start with that percentage test, just so we can get, so we can figure out how good it is now and then how good it is after training, instead of just kind of eyeballing it. So we're going to say, we're going to add another variable, and this is just so you can toggle these for different types of tests as you're playing with it. We're going to do generate score, and we'll default that to true. And I'm going to go ahead and turn live test to false, because that's not what we're working with right now. You can toggle those. If you wanted to, you could also turn these into, command line parameters and run it in the terminal. For me, doing everything through the IDE and keyboard shortcuts, this is just easier. So let's go ahead and do if generate score. Print, I'm going to say generating performance score. We'll do an env. Actually, we'll just copy this, these two. And we're going to remove the render mode equals human, because this time we don't want it to render, do human rendering. We'll do observation info equals env.reset. And we'll need observation size, just like we do in other places, equals observation.shape. That did not need to autofill with all. That needs to be a 0. We'll declare our meta agent equals meta agent env tasks max episode steps equals max episode steps. And then we'll do meta agent dot initialize agent. You see, the cool thing is now that we've got all these classes built out, using them is fairly easy. So we'll do perf score epochs. I'm going to set this to 10. We'll see if that gets us enough data. Total score equals 0. All right, so for I in range perf score epochs. Score equals metaagent.test. And let me go make sure that we did, yes, cool, we returned episode reward. That's what I was looking for. Okay. Total score plus equals score. And then our success ratio will equal total score divided by the length of tasks. And we're doing that because, the score, if we pass in 3 tasks and a score of 3, that's 100%. We don't want that to show up as 300%. So we're dividing total score by the length of tasks, and then we are dividing that by, get one more parentheses in there, dividing that by perf score epochs. So, total score, if we're 100% successful, total score will end up being 30, divided by length of tasks will be 10, divided by perf score epochs, which should get us down to 1. And then we multiply that by 100, which should equal 100%. Again, if we were 100% successful. And then we'll print success ratio, and then we'll just do a little bit of formatting.2f and throw percent in there so it says 100%. All right, let's try this and just see how well we're doing now. And I think I mentioned in the last video that I may have copied in an overly trained model. When I ran through this process the first time, what I got was about 75% before, our sort of finishing room training here, our meta agent training. But let's see what we get. Let's see where our numbers land. Okay, never mind. See, this is why it's important to get some actual metrics, because I was looking at the agent's performance visually and said that I thought it looked too good. But no, it's almost exactly what I expected it to be. 76%, I think I said about 75%. Anything in that area is good. So once we are done with our meta agent training, what you should expect this to be is 95 plus. That's what we're targeting. That's what we're going to try to take it up to. So this is a good time, and I think I mentioned this a video or two ago, but you should definitely go and copy all of your checkpoints somewhere if you haven't already. I did a checkpoints pre-train folder for mine. And the reason you want to do that is because if you mess anything up in this initial meta agent training phase, you're going to ruin your models. And then you'll have to go back and retrain all of them from scratch, which you don't want to have to do. You want to be able to iterate quickly in this stage without having to retrain all of the skills that you just took the time to train. So take a minute, copy checkpoints to checkpoints, checkpoints pre-train, checkpoints back, whatever you want to call it, and then have that available so that you can copy from checkpoints pre-train into checkpoints when, if you need to do multiple runs. You should not be just running, and in fact, every time you run it, you should copy pre-train in. You shouldn't be starting from the last fail. You should be starting from your known good model state. Okay. With that said, warning given, we are going to go into meta agent here, and we're going to go ahead and define our train method. So we'll do def train self episodes batch size summary writer name equals meta agent. Give it a default there. Summary writer name equals runs slash and actually we can go and copy this from the regular agent.py so we don't have to type out quite as much. Let me see how much of this is going to be the same. So we can go ahead and copy from episode steps here up to summary writer name. And we don't need it all. We'll just grab the summary writer stuff. Okay. Some of the other things will be different. Okay. There we go. Less typing. Okay. We'll do updates equals 0 for episode in range episodes. So we're going to go ahead and capture the last action as none. So just like in testing, we have to capture action and last action. We're declaring action way up here because we want it to be available in further down in the code than the loop that it will usually be used in. We'll also do episode reward equals 0, and episode steps equals 0. Print, give ourselves some output, starting episode. All right. Now we start to get into the logic here. So we're going to do a num samples variable. Let's type it and then I'll explain it. Random.choice 1, 2. And what we're doing here is we're setting different goals for the environment. So if you take something that's been pre-trained successfully and you always pass it every single goal. So let's say we have 3 goals. We're doing, microwave, cabinet, burner, and you pass it all 3 goals every single time. What you start to see is some of the individual agents learn other goals. And this was particularly prominent in the slide cabinet because it was relatively easy, especially on the step that opens, the step that turns on the burner. It was relatively easy for that burner turn step to accidentally hit the slide cabinet and get a reward. So, what happens there? Well, you hit the slide cabinet, you get a reward. Now you're starting to learn that that the slide cabinet is where you get the reward, even though that's supposed to be the network for the burner. So it's possible to have some cross-contamination. This num samples setup is going to allow us to say we want either 1 or 2 goals, and then start the environment with those goals in mind. And targeting individual goals without, looking at all 3 tends to, or having a mix of individual goals and then situations where we're going from one goal to the next goal, tends to produce better results for me than trying to target all 3 goals at the same time. Now, there are still downsides to this approach, and the fact that we're still using the same environment is that reward is still attainable, even in situations where the goal is set to something else. I mean, that's just because this goal wrapper is something we implemented, not part of the core environment. But it does mostly offset the problem. So this choosing 1 or 2 goals mostly solves our issue. All right, and that's necessary because you can't change the settings for the underlying environment once it's running. I do have another implementation of this where I passed in a collection of environments, and that collection of environments has every possible, different combination, and then we select from them. That might be something I get into in some of the bonus lectures. So let's go ahead and say for goal in random.sample list self.goaldict .keys. Oh, did I not pass in? I did pass in self. Do I not have a goal dictionary yet? Let's go up. I do have a goal dictionary. So why? Yeah. I don't have random. No, I have random. What don't you like? Expected. Oh, for goal in. And you've seen me do this before. Anytime your editor does not give you the autofill that you're looking for, that's a really good time to stop and go, hey, what did I just do wrong? Because, VS Code is telling me that it no longer understands what I'm trying to accomplish because it can't autofill. And if it doesn't understand it, there's a good chance that I have a syntax issue or a missing import or something. All right, I'm going to choose num samples there. Done equals false. Self.env.setGoal. And that's going to be self.goal_dict goal. Okay, state equals self.env.reset. And then we'll start our training loop here. So while not done and episode steps less than max self.max episode steps. If last action is not none, action equals last action. And we'll go ahead and set last action to none. So basically, if a last action was present, treat it as the current action, and then zero it out. Else action equals self.agent_dict goal.select action state. Okay. Now we get into the training section. If self.memdict goal.canSample batch size. And if any of this looks weird, just remember that, basically we're doing the same training loop that you've seen before. We're just doing it with the various components, the memory, the agent, etc. in dictionaries. That's really at its core, that's all we're doing, is we're doing training goals in dictionaries and cycling amongst different goals. So critic1 loss, critic_1_loss, critic2 loss, policy loss, and see. Actually, let's go look and see exactly what we did under agent. That's what we're looking for. You can just copy this whole block. Okay, that looks good. The only difference is instead of self.update parameters, it's going to be self.agent_dict goal.update parameters. And then I'll also fix self.memdict goal. Okay. Let's see. We don't need, all that looks good. Okay. Down here. We'll go ahead and say next state, reward, done. We don't need those two. Equals self.env.step action. If reward is 1, done is true. Last action is action. So basically, as soon as you've achieved a reward, go ahead and close out that goal. We'll do episode steps plus equals 1. Episode reward plus equals reward. And then mask is 1 if episode steps. Self.max episode steps. Else float not done. Oh, and I missed a 1. I said 1, I just didn't type 1. And that's to ignore the done signal if it comes from hitting the time horizon. Okay. Here we'll do self.memDict goal, store transition, state, action, reward, next state, mask. And again, to come back to the theory of why we're doing what we're doing. So in our standard training, we're always starting from a single place. We're always starting from, the normal beginning position of the robot. What we're not doing is we're not starting at the microwave and going to the light switch, or starting at the cupboard and going to the burner switch. That means that basically the only time that the agent ever sees, itself starting in a different state is during testing. And that can lead to effectively not having enough data on those other states and failing. What this meta agent training does is it's looping through and taking things in pairs of ones or twos, and the twos are what we're really focusing on. And it's doing the microwave and then attempting to do the cupboard, or turning on the burner and then doing the microwave. It's basically the best way I could find to show the agent different transitional states, and get that into the data set. There are other ways you could have done this. You could, go and update, figure out how to update the environment to just start the arm in different positions, and basically force it to get, training data that way. And that probably would have also been very effective. This felt like the closest to sort of real-world training, so it's the approach I took. But I'm sure there are other ways you could solve it, and I would encourage you to. So I'll say state equals next state. Episode reward is episode reward / num samples. And then we'll do some logging. Writer.add scalar. Reward / train. Episode reward. Episode writer.add scalar reward / episode steps. Episode steps. Episode print. Episode. We'll do episode steps reward. Format, episode steps, episode reward. All right. And then finally, if episode %10 is equivalent to 0, self.save models. And let's see if we implemented save models before. Okay, good, we did. We're good to go there. All right. Finally, we need our train meta method, or our train meta script. And I'm just going to start by copying test meta, because that's going to have a lot of the boilerplate code we need. That's going to have all our imports. All of these should stay the same, or at least be similar. Let me look through these real quick. We're going to set episodes to... we need to have an episodes variable. So we don't need live test or generate score. We need to set episodes to 3000. We've got batch size, we've got hidden size, all of that looks good. We have tasks, that's fine, that's exactly what we want it to be. Replay buffer size is good, and let me see what max episode steps, we're going to bump it up to 1500. We're going to give that plenty of time to do some learning. Okay. And then we'll delete this whole section, pull this one over. This is still good. Declaring the meta agent's still good. Initialize agents is still good. We need to go ahead in between here and here and do meta agent dot initialize memory. And we're going to say augment data true. Augment rewards is true. And augment noise ratio equals 0.1. That matches the training that we did earlier. And then instead of here, we can get rid of all this. And we'll just be doing meta agent.train. Episodes equals episodes. Summary writer name equals meta agent A equals alpha. And that's just because that was one of the variables I was playing with, was alpha. You would normally just edit this to be whatever variables you're interested in tracking. And the reason you're doing that is so that they show up in the runs and you can tell which runs are which. So I guess that may have been how I did it, but I don't actually need it this time. You should add whatever variables you want to tweak. If you tweak alpha, throw alpha in there. If you tweak, batch size, throw batch size in there, so that you can track and see, what was what. All right. After training, we're going to do metaagent.save models. And we do have in the meta agent pie, we have a save every 10 steps. So technically that last one should be mostly unnecessary. We should still be capturing snapshots along the way. But if it finishes, I do want a final model save just for cleanliness there. And then we'll do an env.close. And let's see what happens. All right. We are off to the races on training here. I'm going to go ahead and launch TensorBoard. And here, let's refresh, and I'm just going to close everything except for the meta agent so we can watch that one. Now, it's fairly normal, in my experience, for the rewards to fall off for a while. We're asking it to do something a little bit new. We're throwing it in some new positions. We're doing some training before it really gets tuned all the way. So my expectation would be that you see rewards fall for a little while, and then you see them stabilize. And at some point when rewards, stabilize, that's probably when training is done, and you can go back and do your meta agent testing again. So why are we charting both reward episode steps and reward train? Well, at some point when everything is 100% successful, this stops being a useful metric. This just becomes a line, or a line with an occasional drop. But episode steps is actually inversely proportional to how successful your agent is. So, if episode steps is going up, that means that it's taking the agent longer to be successful. If episode steps is going down, then that means that the agent is being relatively successful with fewer steps. And you can see that over here. Like when it hangs, like it looks like it's doing now, yep, we just saw 1,500 steps with 0 reward. So high step count is a hang. And it probably is about to equal lower rewards. So I just went ahead and captured both of those metrics. So, this is a good place to just kind of stop and watch. And here's that dip we were looking for. And at some point, this should crawl back up and kind of level out around high 90s. And that is a good place to stop training. So I'm going to go ahead and pause the video here and let this train for a while, and then come back and finish the conversation. All right, so it's had some time to train. So where did we land? Well, the first run at this, the first meta agent training, did not quite look like we wanted it to. It was very noisy, it was dropping in and out, and that told me that there was something wrong with the process. So looked for mistakes that I may have made, and there were a couple of things that we needed to edit. So one is under buffer.py, and I should probably have variabilized this, but I didn't. I needed to change this from batch size times 500 to batch size times 1,000. The minimum batch size has a different goal here than it did when we were training the individual agents. So training the individual agents, we wanted to figure out a batch size that was inside of our human provided data. Here, we want the current agents to generate a large buffer before they start training together. So we're basically giving it time for the agent to generate what ends up being a 64,000 entry buffer before it starts to do any kind of cross training. So that does need to be batch size times 1,000. And then also in here in the meta agent.py, I originally had this block tabbed over one too far to the right, so it was reporting metrics for every single goal and not for every task. So tab that over to the left, and then ran training, and where we landed was this last one. You can see how much iteration this takes. Even though I've gotten this code working before, and I am basically just rewriting my own solution a second time, when I found a bug, it took, here was the run where I cut the video off, and down here was the run where I finally decided to turn things back on. So it took, 7-8 runs to get back to here. So what did that actually turn into for, success rate? Remember, before we were getting about 76%. So let's run our test script. And we are now getting 100% success on those 3 tasks. It is succeeding every single time. And from experience, if I run this many times, it'll end up with somewhere between 95 and 100%. But either way, much better than the 75% we were seeing. And before we wrap up, let's see one more view of the robot running in full. I went ahead and set live test to true here. We know we were 100% successful, but let's watch the live run and see how it's doing. All right, we turned the burner on. We're opening the microwave, and we have successfully opened a cupboard drawer. With that, I'll see you in part 10, where we'll talk about next steps, how to get in touch, how to get the code base, and what you can do with this project from here. So see you there.